In this week's video, we're going to be covering Chapter 5 on Conditional Expectation. This includes the conditional expectation of y given x is equal to small x, the random variable expectation of y given x, the random variable variance of y given x, and we'll be using this to discuss the important theorem expectation of variance plus variance of expectation. Before we begin, let's quickly recall what we learned in Chapter 4, that is, joint distributions. In Chapter 4, we studied how two random variables x and y behave together. Under this, one of the many topics that we discussed was the conditional distribution of the random variable y given the value of the random variable x. Now, once we know the conditional distribution, a natural question arises. Can we summarize the entire distribution using just one number? And the answer for this is yes. That one number is called the conditional expectation, which simply gives us the average value of y after we know the value of x. If Chapter 4 was about finding the conditional distribution, then Chapter 5 is about finding the conditional expectation. Now let's begin with our first topic. We already know that the expectation means the average or the mean value of a random variable. Therefore, the expectation of y given x is equal to small x means the average value of y given that we already know the value of x. Let's look at the discrete case first. If y is a discrete random variable, the conditional expectation is given by the expectation of y given the value of x is equal to the summation over the range of y times the probability that y is equal to small y given that x is equal to small x. In other words, the expectation is simply written as the value multiplied by the PDF of the function. Here, the conditional probability of y given x is something we already studied in the previous chapter. This is expanded as follows. Let's understand this using an example. We're given a table and asked to find the expectation of y given the value of x is equal to 1. Using the formula, we have written the expectation of y given the value of x as the summation over the range of y times the probability of y given x is equal to 1, and then we have simply expanded our conditional probability function. Our next step is to find the probability that x is equal to 1. As we can see from the table, x is equal to 1 corresponds to the first row. To find the probability that x is equal to 1, we add all of the values where x is 1. Now it's given that we're supposed to find the expectation for those values where x is equal to 1, but the value of y is not specified. Therefore, we take all values of y one by one and add our answers since we have a summation sign. We start at our first value of y, which is given as 10. Then we proceed to the next value of y, which is given as 20. And at last we use the final value of y, which is 30. This gives us our final answer as 19. This tells us that among all of our observations where x is equal to 1, the average value of y is 19. Next, we move on to the continuous case. Suppose x and y are continuous random variables. Therefore, the summation will now be replaced by an integral, making the formula the expectation of y given the value of x is equal to integral over the range of y times the conditional density function of y given the value of x, where our conditional density function is as follows. Again, to understand its application, we consider solving an example. In this example, we are given the joint probability function of x and y, which is 3/8, and we are required to find the expectation of the random variable y given that the random variable x is equal to small x. So we start by writing our formula. Here we have the joint PDF of x, y. However, we don't have the value of the marginal PDF of x. Therefore, we are required to calculate it. Then, we input this value in the above integral. This gives us our final answer as x/2. Unlike the previous example, the answer is not a fixed number. Instead, it depends on the value of x. So as x changes, the conditional expectation also changes. This is because in the previous example, we were asked to find the conditional expectation for a specific value, that is, the random variable x is equal to 1. However, in this example, we are simply given random variable x is equal to small x, where x can be any possible value. This naturally leads us to our next topic. Instead of keeping small x fixed, what happens when we replace it with the random variable x itself? This gives us the random variable expectation of y given x, which is what we'll be studying in the next section. So far, we've been studying the case, the expectation of the random variable y given the random variable x is equal to small x, where small x is a fixed value. Now suppose we don't replace our random variable x by a particular value. Instead, we leave it as the random variable itself. This gives us the expectation of the random variable y given the random variable x as is. Since x is a random variable, the conditional expectation also becomes a random variable. Now if we have the case where the expectation of the random variable y when the random variable x is known to have a particular value small x, then we can represent this as a function of small x. Now that we've simply replaced the fixed value that is small x with the random variable x, this gives us the expectation of the random variable y given the random variable x is equal to the function of the random variable x. So instead of using the particular value as we did above, our conditional expectation is simply a function of the random variable instead. This function is also known as the regression function of y on x. For example, if we found that the expectation of the random variable y given the value of the random variable x as small x is as follows. Then the expectation of the random variable y given the random variable x will be the random variable x upon 2. This tells us that the conditional expectation changes automatically whenever the random variable x changes. Let's now look at an important theorem. The theorem states that the expectation of the random variable y given the random variable x is equal to the expectation of the random variable y itself. This is called the law of total expectation. The idea behind this is simple. First, we find the average value of y for each value of x. Then we take the average of all of those conditional averages. The result is simply the overall expectation of y. There are two ways to prove this theorem. We can either do this using the discrete case or the continuous case. We'll be starting with the discrete case first. We start by using the expectation formula. For this, we sum over the range of x. This is because the expectation of y given x is itself a random variable that depends on x. So when we take its expectation, we average over all possible values of x. Then we go on to substitute the formula for the conditional expectation. Next, we rearrange the summations. Then we expand the conditional probability formula. Once we do this, we notice that we can cancel out both of these terms. This leaves us with. From the previous chapter, we are aware that if we take the joint PMF and we sum it over the range of x, then this gives us the marginal PMF of y. This gives us the exact definition of the expectation of y. Next, we have the same proof but under the continuous case. Now we apply the law of total expectation to two examples, one for the discrete case and the other for the continuous case. Here we start with our first example. We are given the joint distribution table, and using this we are asked to find the expectation of y given x. Hence, we are to find the value of the expectation of the random variable y given the random variable x. We begin with the first part. Now, since the question doesn't specify which value of the random variable x is required to be used, we compute for both x is equal to 0 as well as x is equal to 1. When x is equal to 0, y can either be 0 or 1 or 2. Therefore, we use each of these values and input them into this formula. Similarly, when we solve for x is equal to 1, we get the expectation of the random variable y given the random variable x is equal to 1 is equal to 5 upon 6. From this, we construct a piecewise function. This gives us the expectation of y given the value of x as asked in the question. Now, we move on to the second part. Since expectation of y given x is a random variable itself, we simply take its expectation. So we multiply our random variable here by the probability of x. From here, we've solved both part 1 and part 2. Now, let's look at the continuous example. Here, we've been given the joint PDF, and again, we're asked to find the same quantities. We start with the first part. Here, I've started by writing the expanded form of our formula. To solve this, we are required to find the marginal PDF of x. For this, we simply integrate our joint PDF with respect to y. This gives us our final value as 3x. Then we input all of our values. This gives us our final answer for the first part as x upon 2. Now we proceed to the second part.
Then we input
From here, we obtain the answers to both part 1 and part 2 respectively. Now, we move on to our third and final topic for this video, the random variable variance of y given x and the expectation of the variance plus the variance of the expectation. So far, we've been asking, what is the average value of y given x? Now we ask a different question. How much does y vary around that average given x? Or what is the variance of y given x? This is called conditional variance and it is written as follows. The formula for this is: the first case occurs when we know that the random variable x has a particular value small x. In this case, our formula is given by expectation of y square given small x minus expectation of y given small x whole square. But for the second case, which is what we've covered in the second topic of this video, that is where we have the random variable x which is not assigned a particular value small x. In that case, the conditional variance will be the expectation of the random variable y square given the random variable x minus the expectation of the random variable y given the random variable x whole square. As discussed earlier, this term can also be written as the function of capital X. These are the two forms of writing the conditional variance. After this, we have two more important results. The first result states that the expectation of y square is equal to the expectation of the variance of y given x. plus the expectation of the square of the expectation of y given x. Let's understand the proof. To prove this result, we start directly from the definition of conditional variance. Then we take expectation on both sides. From here, one of the terms that we obtain is the expectation of y square given x. This is equal to the expectation of y square. Then we rearrange our equation, which gives us the final value for the expectation of y square. This gives us our above formula. The next important result that we look at is known as the law of total variance. Under the law of total variance, the variance of y is equal to the expectation of variance of y given x plus the variance of expectation of y given x. Let's look at the proof for this. We start with the previous result and then we subtract expectation of y whole square from both sides. On the RHS, this gives us the variance of y, and using the previous results, we know that the variance of the expectation of y given x gives us the following formula. So we can substitute this formula here, which gives us our final result. From here, we get the formula for variance of y. The fourth result is also known as the expectation of the variance plus the variance of the expectation identity. This is because the right-hand side consists of the expectation of the variance of y given x plus the variance of the expectation of y given x. Now, we look at an example which involves the use of the identities that we've covered above. This example says, suppose the random variable x represents the weather condition. The probability that the weather is sunny is 0.6 and the probability that the weather is rainy is 0.4. Then another random variable y has been introduced. This denotes the number of customers entering a shop on a day. Additionally, we have been given a table. According to the table, on sunny days, the average number of customers in the shop is 10 and the conditional variance is 4. On rainy days, the average number of customers falls to 6 and the conditional variance increases to 9. We are required to find the expectation of y square given the random variable x corresponds to sunny weather, the expectation of y square, and the variance of y. Let's look at the solution for each of these parts one by one. Our first part here involves the first identity that we'd studied. Our first identity was the variance of y given x is equal to the expectation of y square given x minus the expectation of y given x whole square. We rearrange this equation to get it in terms of the expectation of y square given x. Next, we look at the table and insert the appropriate values. The variance of y given x when the weather is sunny is equal to 4. Similarly, the expectation of y given x when the weather is sunny is equal to 10. This gives us our final answer for the first part as 104. Now, let's look at the second part. To solve this part, we use the third identity which we had studied. To calculate the expectation of y square, we calculate both of the elements involved separately, and then we add both of them to obtain our final answer. To calculate the variance of y, we use the fourth identity, also known as the law of total variance. We already know from the second part that the expectation of the conditional variance is 6. To calculate the variance of the conditional expectation, we use the variance formula. Therefore, the total variance is 6 plus 3.84, which is equal to 9.84. That brings us to the end of this week's video on conditional expectation. I'll be back next week on Actuarial Simplified, where we'll be covering Chapter 6 on the central limit theorem. See you next week.